So what we're going to do in this next section is learn about some specific properties of this definite integral. So far, we've just related it to area, but now we have some other tools that we can use to help us out, because everything has been kind of nice, clean cut, a single function. But what if you have a piecewise function? How do you deal with taking the area or an integral of that? So because it's representing the area under the curve, if we kind of have a point in the middle we split it at, say some value of c, one thing we could do is we could find the area from a to c first, and then we could find the area from c to b. Each of those are going to be separate integrals. That's going to allow us to split this up and kind of work in pieces instead. So if I want to integrate from a to b, you could start by integrating from a to c and then going from c to b. So this first integral gives you that first green area. The second integral gives you that orange area. So it's really useful when we're dealing with piecewise functions because they have kind of strange cutoff points, or they have different rules on different pieces of the domain. So let's look at a function that has two pieces. You've got a parabola, x squared plus 4, when x is less than 0. And then we've got a line when x is greater than 0. And we want to find the area over this interval from -2 to 3. So this is where we run into that bit of a problem, because 0 is the cutoff where it switches over to different rules, and I'm integrating over 0. So what we can do is we can look at the graph first. On one half, the left half, you have the parabola. On the right half, you have the line. And they do happen to line up, because if you plug 0 into both, you have an output of 4. So there's no kind of gaps or anything. So we're going to split the integral at the point where it switches over. So when we're going from -3 to 2, I'm going to first go from -2 to 0, which will give me this particular function. And then we're going to switch over and go from 0 to 3, and my output rule is a different function. And that in total will give me the area under this piecewise curve. So for the first integral, from 0 to 2, we're utilizing the parabola. So the function that's going to go inside is the parabola. On the second piece, from 0 to 3, we're utilizing the line, so 4 minus x is going to be the function we integrate over. And now it's just a matter of actually computing these integrals and applying the fundamental theorem of calculus. So we look at the antiderivative of x squared plus 4, which is 1/3 x to the third plus 4x. We're going to evaluate this from -2 to 0. So if you do that, plug in 0 first, you'll get 0 plus 0, minus when you plug in -2. So this will be what you get for plugging in -2. For the second one, you find the antiderivative of 4 minus x, so 4x minus 1/2 x squared from 0 to 3. So you plug in 3 first and then subtract plugging in 0. Then it's a matter of just simplifying. So if you do go through this whole thing, it'll end up being 18 and 1/6. Okay. So this also leads to another idea. Maybe we want to find the area between two different functions. So I've got a region enclosed by some functions f and g. So if I want this area A between the two, I can think of this graphically as I'm going to take the total area under f. So I'm going to take all of this area, and what I want to do is I want to get rid of this stuff to just get the area A. So we're going to subtract the area under G. So the area between the two curves will be the area under F minus the area under G. So this total integral for the area A will be from A to B of the area under F, and we're going to get rid of the area under G. But remember, this was a rule we had. That's just the difference in these two functions. So you're going to take the top curve and you're going to subtract the bottom curve to be able to find the area between these two. Thing you have to be careful about is sometimes you're going to be given bounds, sometimes you won't. So you want to sketch that drawing to be able to clearly know what the top curve is, but you also might need to figure out where those functions intersect to get your bounds. So if they just tell you area between the two curves and there's no x values, you've got to find where those intersect. So let's look at the example. We're going to find the area of the region bounded by the function y equals x squared minus 2x and y equals x. So we have nothing going on. I want to go ahead and I want to find the intersection points of these two because I don't know what x is going to be trapped between. So I want to set x squared minus 2x equal to x. So if I want to solve for the values of x that make this true, you move all the x's to one side, factor out an x. There's two x values where these intersect, at 0 and at 3. So if we graph these two, our line just goes through y equals x, goes through the origin, nice and simple. And then y equals x squared minus 2x, one x-intercept is 0, the other is 2. So your parabola looks like this. So there are two intersection points at 0 and at 3. So if we want the area between these two curves, my bounds are going to be from 0 to 3. And then I want to take the top curve and subtract the bottom curve. So the area A is the top curve, which is the line x, subtract the parabola. So we can clean it up a little bit by distributing that minus sign. And then we have x and 2x, so we really have 3x. So we get the integral from 0 to 3 of 3x minus x squared. So finding the antiderivative is just reversing power rule, and then we want to plug in our bounds. So we plug in 3 first, and then subtract plugging in 0. And then if you go ahead and do the simplification, the area lying between the two curves is 9/2. Okay. So the very last thing we want to do is talk about another application of this. Remember, this area is representing the accumulation of whatever particular thing. So if we're dealing with cost, if we're dealing with profit, it's talking about how your cost is accumulating. So I'm a lot of times concerned with what is the average value going to be. So if we want that, if we have a continuous function over some interval and we want to find the average, which you'll see is y sub AV or AVG, your book uses AB, the way you actually find this value is it's going to deal with the total accumulation. So I'm going to see how much I've accumulated from A to B, and I'm going to divide it by the length of the interval. And so this will tell me on average what my value of x is going to be, or my value of y is going to be. So let's look at a particular example. Let's find the average value of the function y equals e to the x from 0 to 2. So what we do is we look at the length of the interval, so 2 minus 0, and you times it by the area under the curve from 0 to 2. So 1 over 2 minus 0 is just a half. The antiderivative of e to the x is e to the x, so you want to plug in from 0 to 2. So you get 1/2 e to the second minus e to the 0. Well, that's just e to the second minus 1 over 2. So on average, your y value is going to be about 3.19. So really the application for this comes in terms of companies and other realistic things. So if we have an art company that estimates its weekly sales in hundreds of dollars by some particular function, we're going to be concerned, what is my average sale going to be? So what is my average output for this function for the first 5 weeks after it began sales? So in that case, I want to find the average value of this function s. So we need to take the length of the interval, which in this case is the first 5 weeks. So I'm going from 0 to 5. And I want to see what my total accumulation from sales has been, so we integrate from 0 to 5. So that's just 1/5, and we'll plug in what our sales function is. Finding an antiderivative. Antiderivative of 4 is 4t. For t squared, you increase the power to 3, divide by 3, and then we evaluate from 0 to 5. So you plug in 5 first. You get 4 times 5, which is 20. 5 to the third is 125. And then you go ahead and subtract, plugging in 0, but this is just 0 plus 0. So it doesn't do anything. So this is around 12.3, but remember this value is going to be in hundreds of dollars. So it's 12.3 hundreds of dollars, which in that case then you multiply it by 100. Your average weekly sales are going to be $1,233.30.